Hello, welcome to the tutorial of the WaterCROP application that has been built within the RE4AFAGRi project. WaterCROP fits this RE4AFAGRi modeling platform, and as you can see here, the main goal of this application is to evaluate the water needs of agriculture. WaterCROP is an agri-hydrological model able to monitor the crop growth from planting date to harvesting date, and it evaluates on a daily basis the crop water requirement, distinguishing the blue water demand, meaning water from irrigation, and the green water demand, meaning soil moisture, that is rainfall infiltrated in the unsaturated zone where roots are able to uptake water for crop growth. WaterCROP has been developed in this publication, and so you can find more information in this water resources research paper. Is as we say, the water demand module of the RE4AFAGRi modeling platform. The model is a grid-based model, meaning that it works on a pixel level, and specifically it has a spatial resolution of 5 arc-minute. That means a pixel of 10 kilometer by 10 kilometer at the equator. WaterCROP can be run with global coverage. However, in this version, I will show you a specific application for Africa. It runs on a daily basis, and then it aggregates the outputs, for example, the crop water requirement from irrigation on a monthly scale or annual scale, depending on the request. The main inputs variable are climate, soil, crop, agricultural practices, and irrigation equipment. And the key outputs are the crop evapotranspiration, the water stress to monitor the status of health of our crop, the soil moisture, and the irrigation volumes. This is an example of what you can obtain with the WaterCROP model. Here we have calculated the unit water footprint of wheat. So basically, the WaterCROP model can be run in each pixel, and then a total crop water demand can be quantified to understand what is the spatial variability of water footprint or water use. Here you can observe basically where crop water use is more efficient. So, for example, here in this northern part of Europe, or here in some area in the southern part of Africa. While orange pixels, such as here in Ethiopia, show areas where water use is less efficient. So this platform, this software allows you to understand also the efficiency of crop water use. And here you have the irrigation water demand computed by this software. So basically in each pixel, you can assess the water volume required for irrigation. And specifically, the model can be run both for aquifers, groundwater bodies, but also for surface water bodies. You can spot in some places, such as in the US, critical aquifers being depleted due to crop water demand. For example, the California Central Valley or the High Plain aquifer. How does it work? So WaterCROP is based on an agri-hydrological balance, where the key variable are the soil water storage, first of all. So basically the amount of moisture available in the root zone. So for each crop, depending on the rooting depth, there should be introduce as an input variable, we can define a volume of water available along the growing period. Then we need to account for the hydrological fluxes, such as precipitation, that is an input to our control volume defined through the routing depth. Then we need to account for the intersection, that are the amount of water that cannot reach the soil because it is stored or blocked somehow from the canopy of your crop. Then you have a portion of water that is not able to enter the root zone, and this portion is lost as a runoff. So depending on this water balance, where you also have some possible leakage in some specific condition when the soil is above fill capacity, you can have also some loss through deep percolation. So depending on this variable, on these hydrological fluxes entering the control volume, you can evaluate the crop evapotranspiration, so the amount of water needed to grow and to allow the photosynthesis process. At the same time, knowing the evapotranspiration demand, you're able to assess whether this can be met by soil moisture alone, or if you need to consider some irrigation volume. And here you have the equation of the daily soil-water balance. So every day the model evaluates a deficit variable that we call D. This variable is obtained as the algebraic sum of precipitation minus runoff minus actual evapotranspiration plus irrigation. Notice that the crop evapotranspiration is evaluated according to the FAO 56 methodology. Accordingly, it is a function of reference evapotranspiration, which is associated to a reference grass of 10 centimeter height, multiplied by 2 adjusting factor, Kc, that account for the crop properties, and Ks, which account for water stress. So basically, the model starts to monitor water demand in the root zone on planting date. On planting date, we assume that the water demand is at fill capacity, meaning that the crop is under good condition. Then, after some day, due to evapotranspiration, the water demand in the root zone can decrease, and some critical point, some critical water stress can be reached. What is important for the crop growth is not to reach the critical threshold of wilting point. So by monitoring the deficit variable, we are able to provide irrigation every time a threshold predefined is crossed. Once irrigation is applied, as you can see, the D variable goes back to this critical threshold predefined, and the crop can again evapotranspire at the maximum level. The reference year for this computation is year 2017, but depending on data availability, you can choose also a different period. The model is run under both rain-fed and irrigated conditions, and it can allow the consideration of multi-cropping practices, meaning that you can also model the double growing period of wheat, for example, so considering both the spring and the winter wheat. Here, the equation of the water stress coefficient to evaluate the irrigation water demand. The water stress coefficient, Ks, is a function of the total available water content of the density variable we have just discussed, and the difference between the total available water content and the ready available water content. Notice that ready available water content is a fraction of the total available water content, and specifically is the amount of water available in the soil that the plant is actually able to extract. We can also see this relationship in terms of relative soil moisture. or volumetric water content, as it is shown here. And in this case, you have a theta I, which is the daily volumetric content in the soil, the theta wilting point, that is the volumetric water content at wilting point, and theta star, that is the soil water content at incipient water stress. Here you have the quantification of green and blue evapotranspiration. Basically, for each growing period and for each crop, you can evaluate what is the portion of water being satisfied with just the green part, the soil moisture, and what is the amount of blue water irrigation that needs to be added in order to have Ks equal to 1. As you can see, the blue actual evapotranspiration is calculated as ETC, which is the potential evapotranspiration, so evapotranspiration under optimum condition, minus evapotranspiration satisfied by green water. Here an example for the African continent, where basically we assess the irrigation volumes in year 2010, which was our reference year in this case, in this paper that you can also explore online, and the blue water demand by 2040 that should be added to the current infrastructure in order to boost the crop productivity under an RCP scenario number 6. Now, let's move to the WaterCROP app. So basically, depending on whether you have MATLAB installed on your PC or not, you can choose 2 different pathways. In this case, I'm going to show you how to use a standalone WaterCROP app. Basically, with this app, you're able to run water simulation along the entire Africa by selecting an input latitude and longitude, selecting a specific crop, and choosing scenarios of interest. In another tutorial, I will also explain how to use the code. So the 2 main codes developed for the WaterCROP software that, in that case, requires the MATLAB installation. So in order to install WaterCROP, you can double-click the icons, and basically you will have this installation option. So you can basically follow the instruction of this installation option until the WaterCROP app is installed on your computer. So it takes a few minutes maybe to get installed. Once it is installed, you can press finish and you are ready to launch the WaterCROP app.